everyone, welcome to Saimedha Koti-Hyderabad. In this video, I would like to discuss about transformer class number 2. The topic is operation of the transformer under no load condition. In this topic, I will discuss about short notes and concept through questions. So let's start our discussion. First one, we will discuss about the short notes, and after that we'll solve some questions based on this topic. So short notes point of view. So short notes. ఈ టాపిక్లో షార్ట్ నోట్స్ ఏ విధంగా మనం ప్రిపేర్ చేయాలి, తర్వాత షార్ట్ నోట్స్ నుంచి మన క్వశ్చన్ ఏ విధంగా అడుగుతాడు, ఇవన్నీ విషయాల గురించి ఈ వీడియోలో డిస్కస్ చేస్తాను. ఫస్ట్ వన్, under no load condition, transformer draws two current. One is magnetizing current and second one is iron loss component of current. So phasor sum of magnetizing current and iron loss component of current is known as a no load current of the transformer, and this current is also called exciting current of the transformer. And what are the possible questions from this topic? And one of the question is, how do we represent magnetizing current in equivalent circuit, and how do we represent iron loss component of current in equivalent circuit of the transformer? This type of the question. And order of the magnetizing current, order of the iron loss component of current, order of the no load current, order of the no load power factors, and also how to find out magnitude of the no load current, and how to find out no load parameters of the transformer, that is iron loss component, the resistance corresponding to iron losses, and magnetizing reactance. Okay, these are all possible questions from this topic. And let's start from the short notes point of view. One of the short notes. So under no load condition, transformer draws magnetizing current to create the flux, magnetizing current, and iron loss component of the current. IMU is a magnetizing current of the transformer, and IW is iron loss component of the current. And one of the question, next one, magnetizing current. Okay, next question is, next point is magnetizing current. How do we represent the magnetizing current in transformer, and what is the order of the magnetizing current? Magnetizing current is represented with the magnetizing reactance parameters. It creates the flux in the transformer. So the suitable element is a reactance, inductive reactance element. So this magnetizing current, IMU, okay, magnetizing current is represented with XM or X0, represented with XM and X0 in equivalent circuit of the transformers. So this is the one of the question. And next one, order of magnetizing current in the transformer. So there is another possibility of question. Order of magnetizing current, okay, in transformer. So that is order of the magnetizing current is in transformer is from 4% to okay, 6% of the rated current. So this rated current of the transformer. Order of the magnetizing current in the transformer is the 4% to 6% of the rated current of the transformers. And next, another possibility of the question, how do we represent iron loss component of current in transformer? So this, what is the suitable element to represent the iron loss component of the current? So iron loss component of the current, IW, okay, is represented with RC. So where RC is the resistance corresponding to iron losses, or R0, okay, R0, okay, in equivalent the circuit of the transformer, equivalent circuit of the transformers. And next, order of the iron loss component of the current. One more point, order of iron loss component of the current. Order of iron loss component of current. IW in transformer is from 1 to 2% of 1% to 2% of the rated current of the transformer. So this rated current. So this is another possibility of the question. And next, coming to the one more point about this concept. In this case, first one, another one, phasor sum of, this phasor or vector sum of I mu and IW is known as no load current, and it is also called exciting current of the transformer. So that is vector sum of. So this no load current is equal to no load current of the transformer, no load current or exciting current of transformer, or exciting current of the transformer is equal to I naught or I0 equal to vector sum of magnetizing current plus iron loss component of the current. So these are all questions. ఇలా క్వశ్చన్ అడిగే ఛాన్సెస్ ఉంటుంది. అండర్ నో లోడ్ కండిషన్లో ఏ కరెంట్స్ అనేవి ఉంటాయి? మ్యాగ్నటైజింగ్ కరెంట్ అండ్ ఐరన్ లాస్ కంపోనెంట్ ఆఫ్ కరెంట్. మరి మ్యాగ్నటైజింగ్ కరెంట్, హౌ డు వి రిప్రజెంట్ ద మ్యాగ్నటైజింగ్ కరెంట్ ఇన్ ఈక్వలెంట్ సర్క్యూట్? సో ఇట్ ఈస్ రిప్రజెంటెడ్ విత్ XM or X0 element. And next, coming to the another point, order of the magnetizing current in transformer, it is always a 4% to the 6% of the rated current. IW is represented with R0 or RC in the equivalent circuit. So no load current is vector sum of these two currents, magnetizing current and iron loss component of the current. And what is the order of? Okay, this one is another point. So order of the no load current in transformer, no load current, so in the transformer is equal to, so from 5% to 8% of the rated current. So this is order of the no load current in the transformers. And next one, order of the no load power factors. Look at this, order of the theta naught, no load power factor angle. So this 8 short notes, order of the no load current, order of the no load power factor angle, no load power factor angle. So that is denoted by theta naught. It is almost equal to 70 degrees to 75 degrees. Order of the theta naught in transformer is the 70 to 72 degrees. And order of the no load power factors, another one is order of the no load power factors, no load power factor So it is denoted by cos theta naught. So this cos theta naught, and cos of theta naught, it is approximately equal to 0.2 lag. So it is always lagging power factor. Why? Because so it is a lagging. So because this I naught lags the applied voltage by the theta naught. That's why so it is lagging power factors. And next, coming to the another point, another one is the 10th one here. Sometimes we have a question that why transformer has poor power factor under no load condition. So why transformer, why the transformer has a very poor power factors. This type of the question. So 0.2 lag is very poor power factors. Why transformer has very poor power factor under no load? No load daggara power factor enduku chala takkuvaga untundi ani question. So what is the reason here? Magnetizing current. We know the magnetizing current. Order of the magnetizing current is 4 to 6% of the rated current, and order of the iron loss component of current is 1% to 2% of the rated current. So this reason here, so reason for this question, so magnetizing current or iron loss component of current is very less as compared to iron magnetizing component of current. So because of this reason, so theta, so due to which, so due to this what will happen, theta naught will be higher value. When theta naught is high, cos theta naught is the low. So when these two all, as magnetizing current is less as compared to as iron loss component of current is less as compared to magnetizing current, so no load power factor angle will be increases, due to which what will happen, no load power factor angle very low value, so which is equal to 0.2 lag. So this type of the question. And next one more possibility of the question, so that is 11th point. So 11th observation or 11th key point in this topic, and that is vector sum. We know that no load current, magnitude of the no load current. Sometimes we have a question, magnitude of the iron loss component of the current. So magnetizing current, let us calculate magnitude of iron loss magnetizing component of current. It is always I naught current, so into sin theta naught, where theta naught is the no load power factor angle. And the next point, so that is magnitude of, okay, this magnitude, so magnitude of iron loss component of current, magnitude of the iron loss component of current, IW. So that is I naught, okay, into the cos theta naught. So it is I naught is the magnitude of the no load current into sin theta naught, I naught into cos theta naught values. Okay, this is the magnitude of the no load power factors. And next point, so that is 13th question, magnitude of, okay, this magnitude of the no load current. Okay, this how do we get magnitude of the no load current? So no load current I naught is a vector sum of, we know this no load current I naught is a vector sum of magnetizing current, the plus iron loss component of the current, IW values. And by solving this by using vector addition rule, so we will get magnitude I naught is equal to under root of, okay, that is I mu square plus IW square plus 2 into I mu into IW into cos of angle between these two. So that is angle, okay, between I mu and IW values, I mu and I. So by solving here, I naught is equal to under root of I mu square plus IW square. So this is the magnitude of the no load current. So this angle between I mu and IW always is equal to 90 degrees. Cos 90 is equal to 0. So that's why we can get I naught is equal to I under root of I mu square plus IW square. So this is the another point in this topic. We can expect the question from here. And sometimes next one, the 14th one, how to calculate no load parameters, that is R naught and X naught parameters. How to calculate no load parameters? So that is R naught parameters. So that R naught is nothing but the resistance corresponding to this resistance corresponding to iron losses. Okay, this iron losses of the transformer, that is R naught. Sometimes it is also represented with the RC, where RC is equal to applied voltage, okay, divided by iron loss component of the current. So this applied voltage V1 divided by iron loss component of current can be written as I naught into cos theta naught. So this is the formula to find out the resistance corresponding to iron losses of the transformer. And next one, 15th question, 15th possibility of 15th short notes or 15th key point in this topic. So that is magnetizing reactance. Okay, that magnetizing reactance of the transformer. Reactance of transformer. So that is it is represented with XM or sometimes X0 also, X0, XM or X0. So this is equal to applied voltage divided by some magnetizing current, and this is equal to applied voltage into I naught the into sine theta naught. So this is a formula to find out magnetizing current, magnitude of how to calculate resistance, no load current and magnetizing current. And next one more important formula in this concept, that is iron losses of the transformer. How do we calculate iron losses? Iron losses, power drawn by the transformer under no load condition is always equal to iron losses of the transformer. So therefore, iron losses of the transformer are the core losses of the transformer. Iron loss are the core loss of the transformer. So that is denoted by W, this iron losses. So represented with the Wi, sometimes Pi also, iron losses. The sum of hysteresis loss and eddy current losses. Iron losses is equal to applied voltage multiplied by iron loss component of the current. So from this formula, we can find out the iron loss component of current. IW is equal to, so this one is iron losses divided by, so this divided by iron losses divided by applied voltage. Is it correct? Iron losses divided by the applied voltage. We can get, so this iron loss component of the current. So these are all possible questions or short notes or key points in this topic. Our topic is operation of transformer under no load condition. సో ఈ కాన్సెప్ట్, ఈ టాపిక్ నువ్వు ఫుల్ పేజ్గా చదివిన తర్వాత నువ్వు ఈ పాయింట్స్ మొత్తాన్ని రివిజన్ చేస్తే యూ కెన్ ఆన్సర్ ఆల్ టైప్ ఆఫ్ ద క్వశ్చన్స్. సో క్వశ్చన్ సాల్వ్ చేసేటప్పుడు కావచ్చు, లేదా ఆ క్వశ్చన్ ఈ పాయింట్స్ నుంచే క్వశ్చన్ అడిగే అవకాశం ఎక్కువగా ఉంటుంది కంప్యూటర్ ఎగ్జామ్స్లో. అది అసిస్టెంట్ ఇంజనీర్ కావచ్చు, ఏడబ్ల్యూ కావచ్చు, ఏ ఎగ్జామ్ అయినా. సో అందులో ఈ పాయింట్స్ నుంచి ఒకవేళ క్వశ్చన్ ఈ టాపిక్ నుంచి అడగాలనుకున్నప్పుడు నీకు ఈ పాయింట్స్ అన్నీ గుర్తుండాలి. సో ఈ పాయింట్స్ అన్ని నువ్వు రివిజన్ చేసినట్లయితే నువ్వు ప్రాక్టీస్ చేసేటప్పుడు కానీ తర్వాత ఎగ్జామ్ రాసేటప్పుడు కానీ చాలా ఈజీగా క్వశ్చన్ ఆన్సర్ చేసే అవకాశం ఉంటుంది. ఓకే, టిల్ నౌ వీ హ్యావ్ డిస్కస్డ్ అబౌట్ షార్ట్ నోట్స్ ఇన్ దిస్ టాపిక్. నౌ వీ విల్ డిస్కస్ సమ్ ప్రాక్టీస్ క్వశ్చన్స్ బేస్డ్ ఆన్ దిస్ కాన్సెప్ట్. First question number 1, in an ideal transformer, if K is some constant, then the supply voltage is E, supply voltage is V in terms of its magnetizing current IM can be expressed as option 1 JKFIM, option 2 JKF divided by IM, and option number 3 minus JKFIM, and option number 4 minus JKFIM value. So K is constant, it is not a transformation ratio, and K so is given as K is a some constant here, and V is a applied voltage, V1 you can say that the applied voltage of the transformer, and IM is magnetizing current. So this IM is a magnetizing the current of transformer, and next one F is a frequency. So F is the frequency, so this one is the frequency, supply frequency of the transformers. So this was given in this question, and we have to find out, so that is we have to find out applied voltage V in terms of this. What is the applied voltage V in terms of K, the frequency, and magnetizing current? So we know that magnetizing current is equal to, so we know, so magnetizing current I mu the is equal to, so this magnetizing current I mu applied voltage divided by, so in magnetizing reactance JXM, so where XM is a magnetizing reactance one. So this I mu can be written as IM, so that is equal to IM, and V1 divided by J XM value, where XM is a magnetizing. So from this equation we get applied voltage is equal to the J into IM multiplied by the XM value, where applied voltage V is equal to J into IM and xm can be written as the 2 pi fl. So this 2 pi fl, so where v is equal to j im, so this im f, and you can write 2 pi l, and this 2 pi l is a constant, pi is a some finite value, l is a inductance, and 2 is a constant. So this one is equal to j the into im f multiplied by k. So by rearranging these terms, we can get the j k I f okay, multiplied by im, where j is the imaginary term, k is a constant, f is a frequency, im is a magnetizing current of the transformer. So what is the answer for this question? Option 1 is correct, j k f im values. And next one, question number 2. In a transformer, exciting current is made up of two components. In transformer, exciting current is made up of two components, namely magnetizing current Im. So this one is the magnetizing current Im, and core loss component of current is Ic. So that is core loss component of current. With negligible leakage impedance drop, option 1 both Im and Ic. So this Im and Ic lag supply voltage V1 by 90 degrees. Both Im and Ic are in phase with applied voltage V1, and Im lags V1 by 90 degrees, whereas Ic in phase with applied voltage V1. Option 4, Im is in phase with applied voltage V1, but Ic lags V1 by 90 degrees. So this question can be answered by using phasor diagram, and we know, let us consider, so here main field flux is primary flux is taken as a reference flux. So this is the reference. Always magnetizing current is in phase with the flux. So this one is a magnetizing current. Transformer is a pure inductive nature. So that's why applied voltage leads magnetizing current by 90 degrees. So now from this, okay, we can say one more current is required. So that is iron loss component of current. Iron loss component of current is modeled with the resistive element. So current flows in the resistive element always in phase with the applied voltage. So this one is iron loss component of the current. IW. Already have given this one. It is a 1 to 2% of, okay, 2% of the rated current, and this one is, it is a model with the resistive element of R naught ani. Tarvata next, so this is, it is in the order of 4 to 6% of the rated current. So this is the rated current. It is modeled with the element of X0 or Xm. So vector sum of these two, so we can get no load current of the transformer. This vector sum we can get, so no load current. So it is no load current. So vector sum of magnetizing current plus iron loss component of the current. So this angle you can call it as the theta naught. So like this we have here the concept through question means, from this question we need to, I will explain the concept, complete concept about. Suppose if you want to draw EMF induced in the transformer, so in the primary winding, EMF induced in the primary winding lags the flux by 90 degrees, and EMF induced in the transformer in the secondary winding also lags the flux by the 90 degrees. If voltage drop is neglected under no load condition, V2 is equal to V2. So this is vector diagram of transformer under no load condition. From this vector diagram, we can answer this question. See here, and this is denoted by IC also, core loss component of the current, and this is denoted by Im also. So IC in phase with the applied voltage. IC magnetizing current in phase with applied voltage. Sorry, iron loss component of current in phase with applied voltage, and magnetizing current in phase with flux or lags the applied voltage by 90 degrees. Now see the option number 3, magnetizing current lags the applied voltage by 90 degrees, whereas core loss component of current is in phase with the applied voltage V1. So option 3 is correct for this question. Okay, and next let us solve question number 3. A transformer at no load is excited at rated voltage. A transformer at no load excited with the rated voltage. So we are excited with the rated voltage. Now a cut is made in a transformer yoke, thus creating small air gap. So with this transformer core flux, option 1 will decrease and magnetizing current I will increase and will remain constant, and Im will increases as long as Im both as well as Im and flux both will be increases, and also flux and magnetizing current both will decreases. This is our question. So first one, if air gap, there is a small air gap. Air gap is that means reluctancy, okay, reluctancy of the core, reluctance of, okay, core material, magnetic core is directly proportional to air gap length, okay, this one. Because of small air gap, small gap, so it reluctance will be, so because of this one increment, so reluctance of the core, reluctance is denoted by S, reluctance will be increases. So we know flux is equal to, how do we calculate the flux? Basic formula to find out the flux, pi 1 is equal to primary flux of the transformer, pi 1. So that is primary MMF, okay, this primary MMF divided by reluctance of the core, reluctance of the transformer core. So therefore flux pi 1 the is equal to MMF is number of turns multiplied by magnetizing current divided by reluctance of the core. So because your increment in the reluctance increases the magnetizing current in order to produce the same amount of the flux. So that means the here flux is a constant. So this is a as reluctance increases, what will happen? Magnetizing current of the transformer will increases to maintain, to produce, okay, to maintain the flux phi constant, or to produce the same amount of the flux in the transformer. It means that transformer draws extra amount of the current from the source in order to produce the same amount of the flux because of that small air gap in the transformer core. And this is the what is our question? Answer for this question: flux will remain constant but magnetizing current will increases. So option number 2 is correct for this question. And next question, question number 4. Two transformers X and Y with identical ratings and dimensions of dimensions have 0.8 mm and 1.2 mm thickness laminations respectively. If RC and XM are magnetizing branch parameters, RC and XM are magnetizing branch parameters in the equivalent circuit, then option number 1, RC values in both are likely to be equal, but XM of X is likely to be higher than XM of Y. XM values in both are likely to be equal, but RC of X is likely to be higher than the RC of Y. And XM values in both are likely to be equal, but RC of X is likely to be lower than the RC of Y. And RC values in both are likely to be equal, but XM of X is likely to be lower than the XM of Y. So this question is given, both identical transformer, two transformers are there, and the dimensions of, suppose thickness of the transformer X is equal to, so given in the question, thickness of transformer X is equal to 0.8 mm. So this 8 mm, and thickness of transformer Y, so transformer Y is equal to 1.2 mm. So this is Tx and Ty. So two transformer, we know this equivalent no load branch parameters. So this no load branch parameters, it is a no load current I0. It has a two component. So this one is Let us consider magnetizing component of the current X naught, and this is a XM magnetizing component and resistance here, and this is a RC valves. Current passes through here IW, current passes to this branch is a I mu magnetizing current, and so this is applied voltage V1, so is a applied voltage of the transformer. From this equivalent circuit, we can write magnetizing current is equal to applied voltage divided by Xm. Okay, Xm value. So now therefore Xm is equal to, here this one is Xm is equal to, and applied voltage divided by the magnetizing current. So this magnetizing current is independent of the thickness of laminations. Magnetizing current, I repeat once again, magnetizing current is independent of applied voltage. Therefore Xm of X transformer is equal to the Xm of Y transformer. YT means Y transformer and X transformer. So this is Xm are equal. But what about resistance corresponding to iron losses of the transformer? How do we calculate resistance corresponding to iron losses? So we know that iron loss component of the current, IW is equal to, so this one is applied voltage divided by RC. So from here we can write RC is equal to applied voltage divided by IW. So where IW is, in this case, IW directly proportional to iron losses, and this iron loss directly proportional to eddy current loss, and directly proportional to square of the thickness of lamination. Eddy current losses directly proportional to square of thickness of lamination. From here we can write RC, this here RC in this case. So RC inversely proportional to the square of thickness of laminations. Okay. By using this equation, we can say here, so by using this, RC of X transformer divided by RC of Y transformer is equal to, so the thickness of Y transformer by and thickness of X transformer whole square, and this value is equal to, let us simplify now, RC thickness of Y transformer is equal to 1.22 divided by thickness of 0.8, so whole square. So now it is equal to, so we can get, so 4 by so these are 3 and this one is the 0.8. So now we can get the point here 2, and that is a 3 by 2 whole square, and it is equal to, so that is RC of the X transformer. So RC of X trans, I'm writing here, see, by using this equation. So we can write, so RC of the X transformer is equal to, so 3 by 0, so it is a 12 and 8, so that is equal to 3 by 2. So that is a 1.5 square the times of the RC of Y transformer. 1.5 is nothing but RC of X is equal to 15,225. So that is a 2.25 times of RC of Y transformer. So this relation we have. So RC of Y transformer is Z. That means RC of X transformer is greater than the RC of the Y transformer. See option number 2. And Xm values in both are likely to be equal, but RC of X is likely to be higher than the RC of the Y. So option number 2 is correct for this question. Let us solve another question. Question number 5. Transformer at no load behaves like a option 1 resistor, power factor is equal to 0, and inductive reactor, power factor is equal to 0 lagging. Option number 3, capacitive reactor, power factor is equal to 0.82 leading, and option number 4, inductive reactor, power factor is equal to 0.8 lagging. So under no load condition, no load condition, transformer behaves as like inductor. So that is under no load condition, transformer behaves as like the inductor, and power factor under no load condition is equal to power factor, so that is 0.2 lag. Why it is lag? So that is no load current I naught lags the applied voltage, the V1, by some angle theta naught. Order of the theta naught, order of theta naught in transformer, it is nearly equal to 70 degrees to 75 degrees. So cos of no load power factor is equal to no load power factor, that is cos theta naught, and cos of 70 degrees to 75 degrees approximately will get the 0.2 lag. So power factor is 0.2 lagging, and it is act as a inductive reactor. So option the 2 is correct for this question. And next question number 6. In a transformer, primary leakage impedance is neglected, and then these are the statements. Statement number 1, magnetizing current lags the applied voltage V1 by 90 degrees. And statement number 2, core loss current lags applied voltage V1 by 90 degrees. Exciting current lags applied voltage by 90 degrees. Core loss component of current in phase with applied voltage V1. Exciting current lags applied voltage by 75 degrees, and exciting current lags applied voltage by about 80 degrees. From these, the correct statements are option 1, 1, 4, 5, option 2, 3, 4, 6, and option 3, 1, 4, and option 4, 1, 2, and 6. Okay, this is the state. We have to select correct statements regarding this question, and see this question can be solved by using a phasor diagram of transformer under no load condition. Let us draw phasor diagram. So let us take main primary flux Phi1 is taken as the reference quantity, and this is the magnetizing current, always magnetizing current in phase with the primary flux, and transformer is a pure inductive nature, so that applied voltage leads the magnetizing current by 90 degrees. And in transformer, okay, this primary induced EMF lags the main field flux by primary flux by 90 degrees, and this is induced EMF in the secondary winding. Both are in phase with each other. E1 and E2 are in phase with each other. And this transformer, in transformer, iron loss component of current is represented with a resistive element. So current flows in the resistive element always in phase with applied voltage. So this is the iron loss component of the current, IDOM. So vector sum of these two, so we can get no load current, where no load current is equal to the phasor sum or vector sum of these currents, these two currents, iron loss component of current and magnetizing current. So this no load current, another name of this no load current you can call the exciting current of the transformer. Exciting current of the transformer. Now let us verify one by one statement whether it is correct or not. First one, magnetizing current lags the applied voltage by 90 degrees. Magnetizing current is here, and this is applied voltage. Phase angle between magnetizing current and applied voltage. Magnetizing current lags the applied voltage by 90 degrees. So this statement is a correct. And next, coming to the second statement, core loss current lags V1 by 90 degrees. That is core loss current, or this is also called iron loss component of current or core loss component of current, is always in phase with applied voltage. So this statement is a wrong. And next one, third statement, exciting current lags the applied voltage by 90 degrees. So this statement is also wrong. So exciting current means no load current. So this angle theta naught is less than 90 degrees. And fourth one, core loss current in phase with applied voltage. So in phase with applied voltage means this statement is correct. And next, fifth statement, exciting current lags applied voltage by 75 degrees. So this statement is correct. And magnetizing current lags V1 by 80 degrees. It is also not this one. magnetizing current lags applied voltage by 80 degrees. It is not correct, and it is a 90 degrees. Magnetizing current lags applied voltage by 90 degrees. So which option is correct? So 1, 4 and 5. So 1, 4, 5 statements are correct. So option 1 is correct. So this is a class number 2 in the transformer lecture series. So in the previous session, previous video, we have discussed about short notes and practice questions, some concept through questions in the topic number 1, basic concepts of the transformer. And in this video, we have discussed the short notes and also some concept through questions, okay, in the topic of operation of transformer under no load condition. And this and next coming to the another one, yes, to learn complete transformer part like this way. So if you want to learn online or offline classes, so we have offline classes and as well as online. For online class, so you have to download the SpaceGate app, and for more details contact these numbers. So this number is 9848692598, and one more number 9849713451. So every topic, so ఇలా 10 topics or 15 topics ఉన్న ప్రతి సబ్జెక్ట్లో ప్రతి టాపిక్ గురించి వివరంగా డిస్కస్ చేయడం జరిగింది. మరి ఎవ్రీ టాపిక్లో కూడా ప్రీవియస్ గేట్ క్వశ్చన్స్ కానీ, ప్రీవియస్ ఈసెట్ క్వశ్చన్స్, తర్వాత genco, transco, discom questions and practice, every practice questions, ఇలా చాలా క్వశ్చన్స్ టాపిక్ వైజ్గా ఒక్కొక్క టాపిక్లో కొన్ని ఒక 50-60 క్వశ్చన్స్ డిస్కస్ చేయడం జరిగింది. సో అంత వివరంగా చేసిన ఒక ఏ ఆన్లైన్ ప్లాట్లో కూడా ఇలాంటి క్వశ్చన్స్ అనేది డిస్కస్ చేయలేదు. మీకు ఒకవేళ ఇంకా సబ్జెక్ట్ నేర్చుకోవాలనుకున్నప్పుడు సో ఈ నెంబర్స్ కాంటాక్ట్ చేయండి. విల్ గెట్ ఆల్ ద డీటెయిల్స్ అబౌట్ దిస్ కోర్స్. ఐ హోప్ యూ గాట్ ఇట్. థ్యాంక్ యూ వెరీ మచ్.